So in today's lecture we are going to discuss about Einstein theory of heat capacity. So Einstein basically understand the flow in your Dulong and Petit's law. It is basically when you plot the specific heat capacity at your constant volume with respect to temperature. So in the mid-range of temperature, the Dulong-Petit law is followed. That is, your specific heat capacity remains constant from your room temperature to melting point. But at the low temperature, it decreases very rapidly and it follows the T cube law. So thus, therefore, your Dulong-Petit law does not applicable for the low temperatures. So Einstein noticed this flaw and he formulated your another theory of heat capacity. And there is another drawback of your Dulong-Petit law कि ये जो Dulong-Petit law है ये लाइट एलिमेंट्स जैसे बोरॉन बेरिलियम और डायमंड के लिए एप्लीकेबल नहीं है इवन एट योर 20 डिग्री टेम्परेचर है कि रूम टेम्परेचर पर ये लाइट एलिमेंट के लिए भी क्या है फेल हो जाता है. सो बिकॉज रूम टेम्परेचर के लिए क्या इसको क्या रहना चाहिए स्पेसिफिक हीट कैपेसिटी को एट कॉन्स्टेंट वॉल्यूम को कॉन्स्टेंट रहना चाहिए. बट ये लाइट एलिमेंट के लिए क्या हो रहा है ये इसकी क्या है पर्टिकुलर वैल्यू जैसे बोरॉन के लिए है 3.34 बेरिलियम के लिए 3.85 एंड डायमंड के लिए 1.46 किलो कैलोरी किलो मोल इनवर्स एंड केल्विन इनवर्स. So Einstein therefore assumed the following constraints that all the atoms in the crystal are independent oscillators कि वो इन पर्टिकुलर आइटम क्या है उसको हम सिंपल हार्मोनिक ऑसिलेटर यूज एज्यूम करते हैं और ये दे oscillate independently to each other. So each atom has 3 degree of freedom means atom is a 3-dimensional harmonic oscillator. So we assume that there are n oscillator in your solid, so that means the n number of atoms, therefore they have 3n degree of freedom because oscillator has 3 degree of freedom means it is a 3-dimensional oscillator. And from quantum mechanical result the energy of your harmonic oscillator is given by this is the energy of nth level n plus half h mu per when n is equal to 0, that is for ground state for 0 point this is your energy. It will not be 0 at your minimum level, so therefore it is a 0 point energy. And since we know that these all atoms are identical, so therefore these oscillators are identical, so they have the natural frequency same and the energy distribution obey the Maxwell-Boltzmann law. So मुझे क्या लगता है कि जो आइंस्टीन ने एज्यूम किया सो इट वाज ए मेजर फ्लॉ. ये इसकी वजह से कि आइंस्टीन थ्योरी में क्या है कुछ कमियाँ रह जाती हैं वो इस फ्लॉ की वजह से रह जाती है बिकॉज हेयर एंड एज टाइम को हम क्या ले रहे हैं उसकी एनर्जी क्वांटाइज्ड है, दैट मीन्स इट इज़ ए क्वांटम ऑसिलेटर. But Einstein assumed that it follows your classical statistics because Maxwell-Boltzmann is a classical statistics. So you can say that here a quantum oscillator following the classical statistics. And a given energy state can occupy any number of atoms. कि मतलब एक एनर्जी सेल में हम अपनी सहूलियत के हिसाब से जितने मर्जी एटम्स या इलेक्ट्रॉन्स को क्या कर सकते हैं ऐड कर सकते हैं. सो इट हैज़ you can say this is your occupation index. So occupation index is very large. So अब हम क्या कैलकुलेट करेंगे इधर से हम कैलकुलेट करेंगे कि एनर्जी बॉक्स मैक्सवेल बोल्ट्जमैन डिस्ट्रीब्यूशन लॉ लगाएंगे और उधर से हम क्या करेंगे एवरेज एनर्जी कैलकुलेट करेंगे. सो since we know that the number of atomic oscillators having dn energy between having E plus dE at temperature is proportional to your exponential minus E upon kT. This is your the number of atomic oscillator. The number of atomic oscillator Dn having energy between E and E plus D. This is the energy interval at temperature T is proportional to exponential minus E upon kT. So hence from here we can calculate the average energy. So average energy of such oscillators, Dn oscillators, is given by Maxwell-Boltzmann distribution law. So therefore this will be summation from n0 to infinity En exponential minus En kT, where k is your Boltzmann constant. This is question number 1. This is question number 2. Here T is your temperature, En is your energy of nth level, and k your Boltzmann constant, and E this is average energy. So now I have put the value of En here, that is equal to 1 plus half h mu, which is the value energy of nth level. Putting the value of En and En into this equation. So now to solve this equation, we will simplify this by putting x is equal to minus h nu kT. Question number 3, put this into this equation. This will be E bar, this will be h nu this plus half exponential, this will be into, this is whole into, no, there will be no, because it will be observed in this will be n plus half into x. Now we can put the value of your 0, 1, 2, 3, so on. So now here we are putting the value of n is equal to 0, 1, 2. If it is equal to 0, this will be half e raised to power x by 2. If it is 1, this will be 3 by 2, and this is 3 by 2 x, so on up to this. Similarly this, and here you can simplify this by writing this d upon dx log e. If you differentiate this, this will be 1 by this factor, this is here, and another will be, it will be differentiated. So if this is differentiated, this will be 1 by 2 e raised to power x. Therefore this can be written in this simpler form, and this is also here, this is common, and this will be this, and by using the property of log a dot b will be log a plus log b, this is same. And now if you differentiate, because log and exponential are reciprocal, so this will be x by 2 minus, and when you differentiate this, no sorry, this will be x by 2, this will be, if you evaluate this is very simple, this will be log minus this will be minus log e minus 1 minus e raised to power x, and when you differentiate this will be 1 by 2 differentiated with x, this will be 1 by 2, and this will be log 1 upon x, log x is equal to 1 upon x, this will be 1 upon e raised to power minus e raised to power x, and differentiation of x, this will be minus minus plus, this will be e raised to power x. So this factor is here, so now you can write this, take common, e raised to power x is here, this will be e raised to power minus x, this will be 1, and this will be ex, this will be cancelled, and resulting is h mu half plus 1 by e raised to power minus x minus 1. Now put the value of your x is equal to minus h mu upon kt. Now putting the value of x in the previous equation, this will be e raised to power x, this will be minus, this will be minus minus plus h mu upon kt, एक्सपोनेंशियल को ऐसा लिख सकते हैं आप, this will be half h mu, this is what, this is 0 point energy, and it is independent of temperature, because यहाँ पे temperature वाली कोई term नहीं है, so therefore there is vibrational energy even at absolute 0, so this is 0 point energy. So now this is the average energy. So now the vibrational energy of crystal containing an atom is equivalent to the energy of system of 3n harmonic oscillator, because we know that there are n number of identical harmonic oscillator or atoms, and they have 3 degrees of freedom, so therefore there will be 3n harmonic oscillators. So hence the total energy for hence total energy for 3n harmonic oscillators is E bar, E is equal to 3n E bar. So now by using this equation number 4, putting this value into this equation, this will be E, will be putting this 3n h mu upon 2 plus 3n h nu exponential h nu upon kt minus 1. Question number 5. So since this is energies, and therefore specific heat at constant volume Cv will be, we know that this is the rate of change of energy with respect to temperature at constant volume. So अब इसको हम क्या करेंगे, डिफरेंशिएट करेंगे वॉल्यूम से, टेम्परेचर से, तो ये क्या हो जाएगा, बिकॉज इट इज़ इंडिपेंडेंट ऑफ टेम्परेचर, दिस टर्म विल बी 0 प्लस 3nh nu, this will be d on dt, और ये क्या होगी, this term will be differentiated by temperature. So now this is differentiated by division rule, so this will be square of this will be this function, second function, differentiation of first function, which is constant, is equal to 0, this is minus first function, differentiation of second function, and when you differentiate this will be this, and exponential of this, and this will be, because it is differentiated by t, therefore this will be minus 1 by t square, and 1 into this constant, and this term will be 0, so this will be 3n, because here h mu, this will be square, minus minus plus, this will be h nu ka whole square, and टी का भी है तो के का बनाना मेरे को, तो के से क्या करना पड़ेगा, मल्टीप्लाइड एंड डिवाइड, तो दिस विल बी के टी का होल स्क्वायर एंड दिस विल बी एक्सपोनेंशियल एच न्यू अपॉन के टी डिवाइडेड बाय एक्सपोनेंशियल एच न्यू अपॉन के टी माइनस 1 का होल स्क्वायर। अब हम क्या करेंगे, इसको सिंप्लीफाई करने के लिए वी विल डिफाइन ए टर्म दैट इज एच न्यू अपॉन के इज इक्वल टू theta E, which is known as your Einstein temperature. This is your Einstein's temperature. So thus this expression will be much simpler. Thus putting the value of h nu upon t, that is a non-Einstein temperature, into the previous equation, this will become Cb3 n k theta E t upon square whole square exponential theta E upon t divided by exponential theta t minus 1 whole square. So now, depending upon this equation, there are two following cases. First is at high temperature, at very high temperature, that is temperature is very greater than theta E, Einstein temperature से ज़्यादा होगा, so this is your theta E upon T is very less than 1. So this factor exponential theta E upon T 1, इसको हम क्या कर सकते हैं, एक्सपेंड कर सकते हैं, थीटा ई अपॉन टी प्लस हाफ थीटा ई अपॉन टी का होल स्क्वायर प्लस 1/3 थीटा ई अपॉन टी का क्यूब प्लस हायर टर्म्स. Since this t is very big, this term will be very less, so its square will be so much less, therefore these higher terms can be neglected. Because this is small, the small का square और small है, so therefore the higher terms are neglected. So hence this exponential थीटा ई अपॉन टी की वैल्यू क्या होगी, 1 प्लस थीटा ई, तो इसमें पुट करेंगे. लेट अस पुट इनटू दिस इक्वेशन नंबर 6. So now this is at when temperature greater than temperature is lower, so this will be reduced into this term, so therefore we have two terms, 3nk plus 3nk theta e upon t. Additional term is this term. So when t approaches to infinity, t is very large, this term will be 0 because 1 upon infinity is equal to 0, so therefore this term will be 0. Therefore your heat capacity will be reduced to 3nk into this will be 3r, which is nothing but Dulong and Petit's law. So in this case Cb is independent of temperature, so therefore at large temperature your this Einstein expression reduces into your Dulong Petit's law. So there is another case which is for your at low temperature. So at low temperatures, so now we consider this temperature is low, that is your Einstein temperature is greater than this temperature, so therefore your expression exponential theta e upon t, that means this term will be greater than 1, therefore this will be large as compared to 1, therefore this is the dissolution to exponential theta e upon t, this term. So now putting into that equation, therefore this exponential minus 1 will be this, therefore this will be square, and you can say this is the remainder term will be 1 upon exponential theta e upon t, therefore this I have written this exponential minus theta e upon t. So therefore this will be 3r theta e upon t square exponential minus theta e upon t. So since temperature is low, as temperature approaches to 0, so this exponential, this will be exponential 1 upon 0, this will be minus infinity, so exponential infinity is equal to infinity, but this will be 1 upon infinity, Therefore 1 upon infinity is equal to 0. So therefore this approaches to 0. So therefore specific heat capacity also approaches to 0. So as temperature approaches to 0, your specific heat capacity approaches to 0. So therefore Einstein, so hence Einstein's theory of specific heat matches with the experimental facts at high as well as low temperatures. But let me draw the curve. Now your Einstein model matches with your experimental facts at high temperature as well as low temperature. But when you compare your heat capacity of diamond by using Einstein model and your experiment by plotting the experimental observation, so we see that at low temperature your specific heat is experimentally found to be proportional to TQ. However, from this equation, from equation number 7, shows that specific heat capacity is reducing exponentially. It is reducing by TQ and it is reducing by your exponentially. So so we can say that according to Einstein relation, your CB falls rapidly, then it should be at low temperature. Why? क्योंकि यहाँ पे rapidly reduce हो रही है और यहाँ पे क्या हो रही है, it is steadily reducing. So this was your drawback of your Einstein, that it at low temperature it is reducing rapidly because it is exponentially reducing. So therefore this was the main drawback of Einstein model when you compare your heat capacity calculated by Einstein model and your experimental findings. So therefore this was your discrepancy. So that means this figure gives your graphical comparison of experimental value of heat capacity for diamond, which is represented by dots, with the value calculated by the Einstein by dotted line. Here I am plotting this by dotted line by using your Einstein temperature as 1230 Kelvin. So this was the drawback of your Einstein temperature at the low temperatures, and it is due to the oversimplified model employed by the Einstein that all the atomic oscillators vibrate independently at the same frequency. In fact, if you want to remove this discrepancy, you have to assume that your atoms does not vibrate independently, but they vibrate with the coupled nature, means they are coupled to each other, so their vibration of particular oscillator affects the vibration of their nearest neighbor. So that will be discussed in the next lecture, that is the Debye's model of lattice heat capacity.